All right, so the last thing we're going to talk about is this concept of mass percent composition. Okay, kind of sounds worse than it is. Um, so basically, this we're going to for each compound, we're going to be able to tell what element, so for example, for something like sodium chloride, we're going to be able to tell the percent mass of sodium and the percent mass of chlorine in that compound. And we can do that directly from the molar masses of the individual elements and the molar mass of the compound itself. Okay. So for example, we talked about, this is actually for something slightly different, not H2O, but H2O2, which is hydrogen peroxide. So step one, just like we were talking about before, is to figure out what the molar mass of H2O2 is. You're going to grab the molar mass of hydrogen from the periodic table, grab the molar mass of oxygen from the periodic table, and since it's H2O2, you're going to make sure to multiply each of those quantities by 2 and then sum it up. And this should actually be grams per mole of H2O2. Okay, so that would be the total mass of a mole of hydrogen peroxide, right? What if you wanted to figure out the mass percent composition of hydrogen in that sample or in that compound versus oxygen? Well, then you just take your molar mass. Let's color code here, actually. So that one's purple. You're going to be blue. And that gives us our molar mass here in green. Okay. So in order to figure out the percent of hydrogen, you're going to take that same 2 times the 1.008, or really, right, we're going to grab more digits from our periodic table, but this is from the book. And then we're going to divide that by the total molar mass and then multiply it by 100. And this will give us the percent of hydrogen in hydrogen peroxide, rather. Right? And again, that same term that you use to calculate the molar mass of hydrogen peroxide that we sort of had in purple up here, that 2 times the 1.08, that's the same thing that you put on top there. And then in the denominator is just the molar mass of that compound. Likewise, for oxygen, we're going to again divide by the molar mass of H2O2, and we're going to use the 2 times that 16 grams that we got from the periodic table, and that will give us the molar mass of oxygen. Okay, and the two of those should sum up to 100, or pretty freaking close. Maybe the very last digit will be off, but yeah, I mean, just by virtue of how it was calculated, as long as you're not rounding, which is what we talked about, we don't want to be doing, it will always round to 100 or add to 100. Okay, so let's take a look. Let's do one of these ourselves. This is from lithium carbonate, which is actually one of the first mood stabilizer drugs approved by the FDA. We're going to find the percent composition by mass is what they call it, of lithium carbonate, which means that we're going to have at the end the percent of lithium, the percent of carbon, and the percent of oxygen that makes up lithium carbonate. Okay, so the first step is to find that molar mass of lithium carbonate, which is going to be from our periodic table. Whoops. We're going to use lithium, carbon, and oxygen, right? Those are going to be our molar masses. So for lithium, that's 6.941. For carbon, that's the 12.0107, and for oxygen, 15.9994. And then multiply these by however many appear in that molecular formula. So in this case, there are 2 lithiums, there's only 1 carbon, and 3 oxygens. So all of those will sum up to 73.8 0.909, and this is grams per mole. That's the molar mass of lithium carbonate. Okay, so actually just like before, I'm going to sort of color code my chunks here. These were the three terms that went into my molar mass. So if I want now the percent of lithium, right, that corresponded to the blue chunk there. So I'm going to put the 2 times 6.941 divided by the molar mass, the 73.8909. And then I'm going to multiply that by 100, right? So this is the mass of lithium in this compound, and this is the total mass of that compound. And this will get me to 18.79% lithium. Again, if I was being really good, I would do sig figs and how they were followed. Because the molar masses are an addition not an addition, a mixture of addition and multiplication. It makes it pretty complicated. So we're just going to say, let's round these percent mass compositions to 2 decimal places. Okay, so then if I'm going to do percent carbon, I'm going to take the amount of carbon that was in this compound divided by the total mass of this compound multiplied by 100. All right, and again, just to follow where these numbers come from, this would get me to 16.25% carbon. And then lastly, percent oxygen. The oxygen was my purple term. This is going to be equal to 3 times the molar mass of oxygen, the 15.9994, divided by that total mass, the 73.8909. Again, times 100 to put it as a percent. So again, this was just the mass of oxygen in that compound, and this was the total mass. And we're going to get 64.96% oxygen. Right, so that is how we go from the molar mass to the percent mass composition for a given compound. Okay. Now, that's actually the easy part, all right? It's not too hard to go from a molar mass to a percent mass composition. The hard thing, and this is what we're going to work on now, is going the other direction, right? So for lithium carbonate, that's always Li2CO3 because it's an ionic compound. But if we were to take a covalent compound, something that contained carbon and hydrogen, remember that we talked about these subscripts could be a lot of different things. Just by virtue of it being carbon and hydrogen, we can't figure out what it is just by looking at the periodic table, because there are multiple different covalent compounds that exist. So one of the ways that we can figure out is using this percent mass composition. Okay, so that's going to be our goal. We know that we have a compound that has carbon and a compound that has hydrogen. We're trying to figure out what these subscripts are here. How many carbons and how many hydrogens are in that molecular formula? Given the fact that we have 92.26% carbon by mass and 7.743% hydrogen by mass. Okay, how do we take those two pieces of information and figure out what these subscripts are going to be? Okay, step one is we're going to assume we have 100 grams of whatever this compound is. Okay, whatever CH or CXHY, whatever that is, we have 100 grams of it. Well, that would mean that I have 92.26 grams of carbon, because I know that by mass, the percent is 92.26% carbon. And I would have 7.743 grams of hydrogen. right? So that's step one. You're just going to assume that you have 100 grams, which makes it really easy to figure out how many grams of each element you have. In this case, 92.26 grams of carbon because it's 92.26% carbon, and 7.743 grams of hydrogen because it's 7.743% hydrogen. Okay, then I'm going to take each one of these quantities. Now I'm in grams and I'm going to convert to moles, right? So using the molar mass that I get from the periodic table, I can convert from grams of carbon to now moles of carbon. I think carbon was actually pink. And from grams of hydrogen to moles of hydrogen. Now I can compare these, the number of atoms that I have of each one of these. Like the first thing is to sort of think about, I'm going to throw this into a formula that looks something like this. Okay, of course, this doesn't really work. You can't have decimals in a molecular formula. So instead, we're going to keep these ratios the same, the 7.682 and 7.682. Those have to be sort of like relatively the same, but we're going to convert them to a whole number. And you can see that they're the same number, right? So this would be equivalent to having C1, H1, or just CH. You have a 1-to-1 ratio of these two. But let's say that that wasn't immediately obvious. What you would do is you would take your 7.682 and divide it by whichever number was smaller. Again, in this case, they're both 7.682. So H 7.682 divided by 7.682. And that's how I get a ratio of 1-to-1, or again, we would just write this CH. Okay. Notice that this would be the empirical formula of this sample, right? We talked about the difference between the molecular formula and the empirical formula last lecture. Remember, if I had a molecular formula that was like C5H10, the empirical formula would be C1H2 or just CH2, right? You're going to reduce it by any common divisor. Well, judging by how these mass percents work, I will only ever get the empirical formula of my compound out of that. I don't know if this is CH, or maybe it's C2H2, or C3H3, or even C100H100. It could be any of those. All I know is that carbon and hydrogen are present in equal ratios, right? So I can really only get the empirical formula from using the mass percent composition. Okay, so let's do another one here where we're going to have a few more elements involved. Okay, so we have 53.31% carbon, 11.19% hydrogen, and 35.51% oxygen. Well, remember, we're going to assume we have 100 grams, and then that makes it really easy to figure out how many grams of each of these we have. We're just going to go ahead and say the 53.13 grams of carbon in this sample, 11.19 grams of hydrogen in this sample, and 35.51 grams of oxygen in this sample. Okay. Now, how do we go from grams of carbon to moles of carbon? We're going to go look up the molar mass on the periodic table, right? So we go to our periodic table. The molar mass of carbon is 12.0107. So if we took, and again, this book doesn't use all the same periodic table, so its digits are a little bit different, but nonetheless, we can go from grams to moles of carbon using the molar mass. Same thing with hydrogen. Take the number of grams of hydrogen. We'd look up on the periodic table what its molar mass is, and that would help us jump from grams of hydrogen to moles of hydrogen. And then we're going to do the same thing with oxygen. 35.51 grams of oxygen, we can convert that to moles by using the molar mass of oxygen from the periodic table. Okay, so now we have moles of carbon, moles of hydrogen, and moles of oxygen for our compound. Right, and this is a compound that's 53% carbon, 11% hydrogen, 35% oxygen. Now we've converted those values to moles. And so what we get is, if we sort of stopped here, our empirical formula would look something like this. C 4.439, H 11.100, O 2.219. But again, we can't stop there because we can't have decimal places in our formula. So what we're going to do is take each one of those values and divide it by whichever one of those numbers was the smallest, right? So if we're looking, comparing, carbon is 4.439, hydrogen's 11.10, oxygen's 2.219. 2.219 is the smallest of all of those. So we're going to take each one of those numbers and divide it by the 2.219. All right, and then we get, this works out to be 2, this works out to be 5, and this works out to be 1. So then we get the actual empirical formula of the compound, C2H5O. All right, let's do one from scratch together. 37.51% carbon, 2.52% hydrogen, 59.97% oxygen. So right off the bat, we're going to assume we have a 100-gram sample, and that's going to make it really easy to figure out that we have 37.51 grams of carbon, 2.52 grams of hydrogen, and 59.97 grams of oxygen. It's important to note, sometimes people are like, why did you assume you had 100 grams? Just to make it easy. Because if I assume I have 100 grams, then I know that I have 37.51 grams of carbon. I could assume I had 5 grams. I could have assumed I had 1,000 grams. I could have assumed any number. I would just then have to do a little math to figure out how many grams of carbon that was. So if we do 100 grams, it makes it really easy to figure out how much of each we have. Okay. So then I'm going to convert from grams to moles. Again, using these same values from the periodic table. We'll actually pull these numbers so we can get used to using all of our digits. So that's the 12.0107 grams of carbon in 1 mole of carbon. Hydrogen, 1.00794 grams of hydrogen in 1 mole of hydrogen. And 59.97 grams of oxygen. I want to convert that. I'm going to use the 15.9994. And notice that I know that I'm dividing by the molar mass, or rather I'm using the inverse of this particular quantity because I need grams to cancel and to be left with moles. Okay, so again, sort of how we're going to do this is we're just going to take all of our digits. For the one thing that's nice about these percent mass composition problems is at the end you'll work out with your empirical formula with all whole numbers. So you don't have to worry about sig figs at all throughout this problem, but you do want to make sure that you're copying down a bunch of digits so that you don't incur any sort of a rounding error. So this would be 3.1230. We could probably stop there. Bottom line is the more digits you copy down, the more likely you are to get to not have any sort of a rounding error. 1, 4. And this is now moles of carbon. This is moles of hydrogen and 3.74826 moles of oxygen. Okay, so if I stopped here, I would have C 3.1230. Oh no, I'm sorry. H 2.500, 3.748. But of course, I can't stop there. I need to, because I can't have these fractional numbers, so I'm going to have to take them and divide by whichever one's smallest, 2.500, 2.500, 2.500. And again, you really want to take this number and divide it by this number with as many digits as possible for this to work out. And what we're going to find is when we do that, so this is actually, we're going to have an additional step for this particular problem compared to what the last one was. What we get is C 1.25, H1, O 1.5. Okay, so we got one of these to be a whole number. That's that hydrogen. That's actually why we divide by the smallest one. What we don't have are the other two are not whole numbers. Okay, I have to get them to be whole numbers before I can stop. So what I'm going to do is I'm going to take everything here and multiply it by 2, all of those subscripts. And I'm going to keep on playing this game until they're all whole numbers. So let's just do this one, multiply it by 2, we get C 2.5, H 2, and O 3, right? Notice how, again, the 1, I multiplied that by 2. The 1.5, I multiplied that by 2. The 1.25, I multiplied that by 2. Each subscript, I multiplied by 2. And now, both the hydrogen and the oxygen are whole numbers, but carbon is still not a whole number. So I got to do another round. I'm going to take it and multiply it by 3. So now I have C 3.75, H 3, O 4.5. All right, those aren't all whole numbers. So now I got to take it and do it a 4th time, multiply everything by 4. Now I get C5, H4, O6. Now they are all whole numbers, so I can stop. And my final answer for the empirical formula of this compound is this right here. All right, so notice that this was a little bit more complicated than the last process in that after I got to this step here and I divided by whichever number was smaller, I still wasn't left with all whole numbers. So what you got to do is take everything, multiply it by 2. Are they all whole numbers? No? All right. Take everything, multiply it by 3. Are they all whole numbers? No? All right. Take everything, multiply it by 4, etc., etc. And that's how you're going to get to your empirical formula. Now, again, I can only ever get to my empirical formula by doing it this way. But I could potentially figure out what the actual molecular formula is if I was given one more piece of information, which would be what the molar mass of the actual compound is. Because if I have my empirical formula, I can figure out the molar mass of the empirical formula, take the molar mass of the whole thing, divide it by that, and that will give me some whole number that I multiply my empirical formula by. Okay, so let's just see an example here. In the compound that we originally, like for the very first example, remember we figured out that the empirical formula was CH. Well, if I told you that this compound actually had a molar mass of 78 grams per mole, then you could figure out first, use a periodic table and figure out the molar mass. So this would be the molar mass of CH, or the molar mass of the empirical formula. If I take 78 and divide it by that, I get 6, or 5.99, which rounds to 6. Rounding in this type of equation is really weird. You only round when you're already really, really close. Right? So for example, what actually popped out of my calculator last time was 1.499. I said that that was 1.5. If it was something like 1.40, I wouldn't be able to round it. It has to be really, really close. And I'll make sure to choose numbers such that they're very, very close. Okay, but so you get 5, which is, basically 6. So then you take this whole formula, C1H1, multiply it by 6, and you would get C6H6. That's the actual compound that you have. So if you're given this additional piece of information, which is the molar mass of the compound, then you don't have to stop at the empirical formula. You can actually go all the way to the molecular formula. So let's do an example here. This compound is 30.45% nitrogen by mass and 69.55% oxygen by mass. So that means I'm going to assume I have 30.45 grams of nitrogen and 69.55 grams of oxygen. I'm going to use the periodic table. Nitrogen and oxygen in order to convert to moles. So this is 14.00674 grams per 1 mole. Likewise, 15.9994 grams per 1 mole of oxygen. So this would take me to 2.17395 moles of nitrogen and 4.34703 moles of oxygen. That gives me this kind of rough empirical formula to start out with, but I'm going to take that and divide by whichever number is smaller. In this case, it's that 2.1739. And now I get an empirical formula of N10 1.999. Again, that's close enough that we're going to be able to round that to 2. So my empirical formula is NO2. It's the empirical. But I'm now given another piece of information, which is that my compound actually has a molar mass of 92 grams per mole. Well, if I were to calculate the molar mass of the NO2, I'm going to just kind of give the answer here. You guys can make sure you understand how I got this number. That's 46.00554 grams per mole. So if I took my, take my 92 grams per mole, that's the molar mass of the molecule, the compound, divided by the molar mass of the empirical 46.00554 grams per mole, I'm left with 1.9997, which again, we're going to call 2. And so what I'm going to do with that 2, this is how many of my empirical units, so to speak, are in that molecular formula. So I should take my NO2 and multiply each of these subscripts by 2, giving me N2O4. This would be the molecular formula of this compound, right? So just given the mass percents, I can find an empirical formula. But then if I want the actual molecular formula, I would need to be given another piece of information, which is the molar mass. Using the molar mass of the molecule compared to the molar mass of the empirical, I can figure out what my molecular formula should be.